China. Okay, so what we have here, here's a light bulb, and these represent wires. So the black lines are the wires. The X's represent a magnetic force that's going into the board. And this this black thing here represents a conductive piece of metal that is touching the wires so that it has the potential to create a circuit. So all of the wires are connected and it creates a circuit. Although if we move this now, the circuit's not connected so that no electricity could flow through the circuit because it's not a closed circuit. But when I put this here, we're imagining that the circuit is closed. So again, the X's represent a magnetic field going into the board. So what we're going to learn in a little bit after this, which is called the Lenz's law, we kind of talked about this earlier, about the magnetic flux that we talked about yesterday. But basically what happens is if we move this bar down these tracks of wires, what's going to happen is through no outside influences, like there are no batteries attached to this or anything, but if I move this current, if I move the conductor down the wires, it's going to induce a current in the wires. And as it turns out, if I move, the way this is set up, if I move it to the right, then the current is going to be going counterclockwise through the circuit. So if I move to the right, now if I move to the left, then, so if I, rather than increasing how much magnetic field is going through it, if I decrease the amount of magnetic field going through it, the current is going to go in a clockwise direction. And remember, it's passing through this black bar here. The black bar is like just another piece of wire that's connecting things. So if I move it, nope, not everything, just this. If I move the black bar to the right, there's going to be a counterclockwise current, and if I move it to the left, it's going to be a clockwise current. Okay, so yesterday we talked about two loops of wire. If we moved one closer to the other, let's see if I can draw some loops in perspective today. Let's see if I learned anything. So this, if I want this side to be backwards, it's skinny. That is that enough? Okay, yesterday we talked about how, keep in mind these are really wires, and they're not actual rings, they're wires, and they're really thick wires. So they're not, I should have drawn them with a hole at the bottom. There we go, now there are wires connecting it. So let's say that there's a current going in this direction through this wire. We learned yesterday that the magnetic field would be pointing this way. And we talked about how if we move this ring of wire, or this ring of wire closer to the other one, that Mother Nature is going to resist the new flux of the magnetic field. So we're getting, remember, flux is amount of stuff passing through.
Yes.
Of stuff passing through. So if these two things are really far away, then there's no magnetic field passing through this one because we haven't put a current through the wire. But while we are bringing this one closer, Mother Nature is saying, oh, there's more magnetic field coming in through here, and I don't like it, so I'm going to make a magnetic field that's going to be pushing in the opposite direction. No, remember, that's only as I'm pushing it closer. Once I stop moving it, the current's going to drop back to zero, so that there's no more current. So it's only as we're moving it, just like if we have a magnetic field and a charged particle in it, that particle has to be moving to get a magnetic force. If it's not moving, then there's no force. And there's some really nice math formulas that prove all of that, but you have to have several more years of calculus to understand them. That's why we didn't do anything like that. That's why I'm just telling you these things as facts. So just like Mother Nature is trying to resist the influx of a larger magnetic field, what's happening with this bar is that as I'm moving it to the right, I'm increasing the amount of magnetic field that's going through this wire, or this closed loop of wire that we have here. Remember, the bar makes it a closed loop. So that as I'm moving it to the right, I'm increasing the magnetic flux just like I would be when I'm moving the ring closer to the other ring. And if I'm moving the bar to the left, that would be just like I'm moving the ring away from the other ring, in which case, I don't remember if I said this yesterday, but if I started with the rings close together, right now there's a lot of magnetic flux going through the ring on the left, but as I move to the right, I'm decreasing the amount of magnetic flux, and Mother Nature doesn't like that, so it's going to try and push magnetic flux in the same direction, so that would induce a current. This is all about induced current. And what it means by induced current is current that's not provided by a battery. So again, there are no batteries hooked up to this little light bulb. So again, as I'm moving to the right, the light bulb would light up, but then once I stop moving the bar, the light bulb stops producing light. And if the light bulb is the kind that can do AC current, then it will also light up as I move it to the left.